Right. So, hello everyone. Thanks for the invitation. And so, my name is Gongjun Choi, who is working as a postdoc in Cheongdao Lee Institute (TDLI). The today's topic that I'm going to talk about is cosmic birefringence and electroweak axion dark energy. And this talk is based on the work in collaboration with the Weikang Lin, Luca Visinelli, and Tsutomu Yanagida, for which you can find some relevant paper in archive this number. Right. So recently, non-vanishing rotation angle of CMB linear polarization was reported, and that rotation angle reads 0.35 degree with this uncertainty. And it turns out that a pseudoscalar field, if there is, which is a coupling to the photon via this dimension 5 operator, and that it can induce non-vanishing rotation angle of CMB linear polarization, of which expression is given by this here, where the C gamma is anomaly factor of this dimension 5 operator, and the T0 is today's time, and the TLSS is the time defined at the Laskin surface. And FA is an X indicate constant. So for the case with the effective Lagrangian of the axion, uh, the easiest way to have ordered 0.1 rotation angle is the variation of the field in axion field amounts to the ordered 0.1 times axion decay constant. And this can happen when you have a slow roll scenario with the initial field value evaluated at lasting surface is very near the hilltop, pi times decay constant of axion. And if this is a case in this case of slowly rolling down axion scenario, and then the C gamma as large as 10 may make this expression comparable to the 0.30 observed value of 0.35. And in that case, you can immediately realize that the corresponding axion's equation of state would be probably lie somewhere between the -1 and 0, because axion potential magnitude is easily dominating over the kinetic energy. And then this observation makes us pose a question for whether the observed cosmic birefringence is a hint for the quintessence type dark energy. So if we take cosmic birefringence as a hint for the axion dark energy, and then one of the important question is, can we produce the axion potential, which is comparable to today's observed energy density of cosmological constant? And when an axion couples to the instanton with the instanton action given by 2 pi divided by alpha, where alpha is a gauge coupling squared divided by 4 pi, and rho is the instanton size. The instanton of size rho generates the potential quantum mass 54th and minus instanton action exponentiated. So for matching this axion potential to currently observed energy density of cosmological constant, which amounts to the 2 times 2 millielectron volt naively, roughly, it turns out that we figured out we can numerically figure out that the required alpha to have for this matching successively amounts to the 1/44. So if you look at MSSM, then you can easily realize that the SU2 gauge coupling, when it is evaluated at Planck scale, that amounts to 1/23, which is very close to this required value for having the axion dark energy. On the other hand, when axion mass is 10 to the minus 33 eV and axion decay constant is order 10 to the 17 GeV, you can easily check that the observed energy density of cosmological constant is very comparable to the axion mass times axion decay constant squared. So this may give us the hint that the electroweak axion with mass 10 to the minus 33 eV comparable to today's Hubble expansion rate and axion decay constant of order 10 to the 17 GeV in MSSM can serve as quintessence type dark energy if electroweak instanton with size inverse of quantum mass dominantly generate the Axion potential. So then as a particle physicist, the natural question that we could impose immediately after this realization would be, can there be any consistent particle physics model for electroweak axion as a candidate for the quintessence type dark energy? As a matter of fact, in 2000, Nomura Watari and Yanagida already proposed the electroweak axion dark energy model based on the following symmetry group, which raised the standard molar gauge group times the discrete R symmetry Z4R and Yuan Frogan-Nielsen type global symmetry and Yuan global symmetry, which is anomalous for the SU2. And when you have a particle MSS and particle contents plus some SU2 charged heavy degrees of freedom, and you can easily check that these particle contents make Z4R anomaly free with respect to the standard molar gauge group. And then with the appropriate charge assignment, which you can check in our paper, you can see the superpotential is given by this form, where W here is the Schwarzschild field for the vector multiplets, and phi is a characteristic field for the PQ scalar. Psi is a characteristic field for the heavy quark, and tau is the Spurian field for the holomorphic gauge coupling and gauge no mass. And given this superpotential, one can easily realize that once this anomalous Yuan global symmetry gets spontaneously broken down, we can have effective superpotential, which couple the axion characteristic field to the SU2 vector supermultiplets. Okay, so it turns out that the Axion potential is dominantly generated by the effective Keller potential multiplied by e to the minus 8 pi squared times tau. And if you actually work on writing down the effective Keller potential, you come to know that the symmetries constrain this effective Keller potential to make it depend on two super covariant derivatives, which explain the R charge 2, and which provides mass dimension 2. And also, you can figure out that the effective Keller potential depends on inverse power of the instanton size. And then, because of this, it turns out that the instanton-induced superpotential dominantly generated by Planck-sized instanton, whose expression in the end is given by following expression here, where alpha 2 is a gauge coupling of SU2, and M SUSY is a soft SUSY breaking mass, soft mass for SUSY breaking, and epsilon here is a Spurian field, which breaks the Yuan Frogan-Nielsen symmetry, which we introduced in order to avoid rapid proton decay. And this expression, you can easily check when epsilon is 1/17, which is required for correctly produced in the quark masses, can be successfully matched to the observed the energy density for the cosmological constant. So so far we have discussed how the model can produce the observed energy density for the cosmological constant. So with that being said, now we next move to the question for whether we can have a slow roll condition satisfied. So for this condition to be met today, it turns out that it's better to have axion decay constant close to Planck mass. On the other hand, Weak-Gravity conjecture sets the upper bound for the instanton action, which is given by the Planck mass divided by axion decay constant. And for the case where the axion decay constant is very close to Planck mass, it turns out that the required gauge coupling for SU2 evaluated at Planck scale needs to be very close to order 1 quantity. which is, by the way, greater than the alpha 2 at MSSM, which is 1 over 23. So this means in order to have solar condition satisfied, and also simultaneously in order to satisfy the weak gravity conjecture, an upper bound of instanton action, we have to introduce some heavy degrees of freedom to modify the RG of the SU2 gauge coupling so that we can have alpha 2 amounting to order 1 quantity at Planck scale. So to avoid, in other words, to avoid fine tuning of initial value of Axion and to satisfy the slow roll condition today, so we feel it's necessary to introduce heavy degrees of freedom charged under SU2. And for our case to do this, for simplicity, we introduce triplet sigma and sigma prime with order 10 to the 7 GeV mass. And then we realize alpha 2 comparable to order 1 at Planck scale can be achieved. But then once we modify our particle contents in UV regime by introducing these SU2 triplets, one may have a concern and ask a question about whether there can be distortion of our prediction for the axion potential magnitude, which is very important for matching to the observed energy density for the cosmological constant. However, it turns out that when we introduce this heavy degrees of freedom charged under SU2, because the zero mode, fermion zero mode of these heavy fermions charged under SU2 will be emitted from the SU2 instanton. We have to close those new fermion zero modes, and for that we have to do, and we do that by inserting masses. And it turns out that these additional factors to axion potential magnitude, which we have here because of closing new fermion zero mode, will precisely cancel the modification to the gauge coupling, RG, so that it turns out that this UV structure change due to additional heavy degrees of freedom will not change the model's prediction for the axion potential. So our prediction for the axion potential, which is matched to energy density of cosmological constant, remain intact, even if we make some change in the UV structure, particle contents, UV structure and particle contents in the UV of the model. So in sum, the modification of the RGE of alpha 2 that is precisely canceled by new factors, including heavy fermion masses. So far, the model succeeds in producing energy density for dark energy, and also the model succeeds in making slow conditions satisfied with axion decay constant comparable to the Planck mass, and the alpha 2 evaluated at Planck mass comparable to 1. Then getting back to our original motivation for this work, we ask one of the most important question of our work, which is can this electroweak axion dark energy, can it explain the rotation angle of CMB linear polarization plane, which is 0.35 degree. And it turns out that in current model, the anomaly factor is 1. And as I said, this 1 is not enough to have order 0.1 rotation angle here. So to make this expression comparable to order 0.1, we introduce additional heavy degrees of freedom, which are charged both under the U1X global symmetry and U1 hypercharge gauge group. And by doing that, we can induce increase in the anomaly factor C gamma. However, on our introducing this extra omega fields to increase C gamma, it turns out that the beta function for the U1 hypercharge gauge coupling increase with the increasing number of this omega field here. So we realize that in order to make the U1 hypercharge gauge theory perturbative, there must be upper bound of number of newly introduced heavy degrees of freedom omega. Um, so then we, by setting initial time derivative of axion field on the hilltop, 0, and by scanning over different values of V0 and Fa, we tried to numerically solve the equation of motion for this axion field. And then based on that, we obtained the relation between the beta over C gamma and the equation of state for the axion field here. And here the C is a numerical quantity that we find in our trial to numerically solve this equation of motion, whose value is listed here as a function of axion decay constant over quantum x here. And importantly, this relation between the equation of state of dark energy, axion, and the beta over C gamma can be used for any other quintessence axion type model. So now, given this relation that we derived in our solving this equation of motion, if we apply the existing constraints on equation of state of dark energy, quintessence type dark energy coming from Planck collaboration, and also if we apply the theoretical upper bound for C gamma, ensuring the perturbativity of Yuan hypercharge gauge theory. And then we eventually obtain the constraints on C gamma for every different value of Fa over M Planck. So this is the region in this plane, which is consistent with first cosmic birefringence, and also constraints on equation of state of quintessence type dark energy, and also consistent with the perturbativity of the model. So given this constraint on C gamma as a function of Fa over MP, if we apply this constraints on C gamma to our derived relation between equation of states and beta over C gamma, and then we can obtain the prediction for the equation of state of axion dark energy of our model. And we find our axion dark energy will be characterized by the equation of state lying between minus 0.1994 and upper bounded by minus 0.968. All right, so here's a summary of today's talk. So cosmic birefringence can be a strong hint for the quintessence dark energy. Electroweak axion can be a candidate for the quintessence dark energy with mass 10 to the minus 33 eV and axion decay constant of order 10 to the 17 GeV. And as I emphasized, the model's prediction for axion potential magnitude, sorry, this is to the fourth, matched to which is very well matched to the observed energy density for cosmological constant. This prediction is very insensitive to the UV structure of the model. So whatever particle contents you newly introduced in UV regime, in order to distort the gauge coupling for the SU2, that doesn't really change our prediction for the magnitude of the axion potential. And explaining the observed rotation angle of CMB polarization plane, 0.35 degree, our model was shown to predict this range of equation of state of axion dark energy. And in future, if uncertainty of this rotation angle becomes reduced to 10 to the minus 2 level in future CMB mission, and then we're gonna have improved prediction for the our quintessence type electroweak axion dark energy, which is from minus 0.982 to minus 0.961. Right, so this is the end of the talk.